thanks to the organizers for giving me the opportunity to present the work we're doing. As was mentioned, we've been already 2 years investigating the use of machine learning in the analysis of the archives. I'm going to give you, along with the ride that we've been having, fascinating ride into the details of the archives with the hand of these powerful tools. And I hope I will convince you that there's huge potential future in all this work. But let me first start by introducing my colleagues here. In particular, I want to emphasize the work of Sander Kroek, who's a research fellow at ESTEC in the Netherlands, and Pablo Garcia Martin, a PhD student with us from UAM. Also, I want to acknowledge Maggie Liu, a former research fellow at ISAC, who started sort of planting the seed in our minds about how would it be like to use these machine learning algorithms. And I also want to acknowledge Ross Thompson and Samet Karadak from Google, who are helping us to actually apply and deploy some of these models in Google Cloud to be able to get faster to certain results. I'm going to show all of that in a minute. And of course, all the other people that have contributed to this work are listed here. So our motivation is to enable data-driven astronomy. Why is that important? I'm going to try to justify in a minute, but let me tell you that we are convinced that this is going to be a game changer completely for astronomy and for science in general. I'm going to then show you an example and some of the nitty-gritty details of how is it like to apply AutoML, one particular brand of machine learning algorithms, to identifying asteroid trails on Hubble images. And then I will end up by sharing with you my vision of how the future might look like and how might all these technologies change the way we do astronomy. So the goal, as I was saying, is to enable data-driven astronomy. So you can wonder what do you mean by that? Okay, so putting things in context. When I started my PhD 20 years ago, my thesis advisor, who you can see here, Benja, explained to me that retrieving an ultraviolet spectrum from the IOE satellite 10 years before, so well before the internet times, typically would require like 6 months. He would send a letter, he would get a pile of papers with the wavelength and fluxes, and then he would have to type all these things into his own computer to be able to actually visualize the spectrum. Today, that takes 1 second, right? So, of course, things have changed so much, and we are sort of adapting to this change, but definitely technology is going ahead of us humans in this. So one can wonder, how will astronomy be done in 30 years from now, and how do we get there? Okay, so data volumes today, here you can see in this figure how data volumes are growing as a function of time. Of course, the argument to make here is that astronomers, to analyze this data, are not growing that fast, right? Absolutely not. And so while today astronomers are competing for data, in the future data will be competing to get users to look at them. Even more in the midterm future, when data volumes are going to grow to on the petabyte scale for astronomy, in which case there's going to be such a huge amount of data that, I mean, there's not going to be unless people is equipped with really powerful data number algorithms, that people can actually look at all this data. Astronomy is actually slowly becoming a data-driven science. This figure you see here shows the publications from the Hubble Space Telescope as a function of time in 3 categories since the launch year, which was 1990. And then you can see these purple and yellow bands there, which are papers, so science results that have been published by people who had nothing to do with those who requested the observations to be taken, right? Which is something really important. Let me pause here for a second to just make you realize that more than half of the scientific production of the Hubble Space Telescope is not coming from space. It's actually coming from the ground. The data archive itself is the scientific resource. And it's not just that. Let me tell you, data is complex, and there's so much that it really makes it difficult to grasp. So let me show you about this application we have called ESA Sky, which you can find in sky.esa.int. Here we've made an effort to make all this data available and easily browsable on a web browser by anyone. So here we've gone to this galaxy, and we're looking at it as a function of wavelength from the X-rays to the mid-infrared, and it just takes a few seconds to visualize all this. Now we can explore how many observations there are, and now I'm just pulling all the Hubble observations ever taken, and you can see all these outlines. These are all Hubble observations. I can also look at all the publications. So all the sources for which there's at least one scientific paper can be visualized together with all this data. Okay, so you can see that the amount of data that we have available for the astronomers. Now I'm putting all the data that we have from all these observatories together in a single all-sky map. You can see the galactic plane in the center and the ecliptic in this, in this inclined bar. And then you can also do the same with CADC data, with data from MAST and data from ESO. So you can see that just in a few seconds, I can access literally terabytes of data. So users really need to have tools to be able to cope with this complexity, because there's no way they can really look at all this data themselves, right? Definitely, I would definitely encourage you to all go and explore this. It works on your phones as well. But I want to make the point that we need to go from the traditional workflow of a science paper where people, which was theory driven, right? I had this scientist would have an idea, what if nature works like this? And then he would have to ask for time to observe certain objects and then make a comparison between the data they got and their theory, and then revising eventually whether this still matches with all their existing data, publishing the result, and of course they would get fame and glory, and then they would, the cycle would continue. But I want to argue that we just need to move into a new, more industrialized data analysis paradigm, where we actually have the raw data, which we need to prepare to be able to use it in training models that represent our physical description of what nature is like. Then we need to deploy these models such that we classify data as it comes, and then what we learn from that classification, then it modifies the new data we obtain. So this new cycle is the industrialization of the scientific method, if you want. So how do we get there? Well, we thought about this, and I'm going to tell you our vision of how we will automate classification of archival images. So let me first start by giving you a very quick description of what a convolutional neural network works like. There are 3 layers, typically a convolution layer, a pooling layer, and a fully connected layer. So imagine we have this 3x3 pixel image that has an X, right? The orange is the image. And I want to train my computer to discover that that's an X. What I do is to make a 2x2 pixels window and scan the image. And here you see in this convolution layer. And then whenever I see a match between my little window and what it's in the image, then I mark as relevant information. Then once I have this, I go to the pooling layer. That's where I say, all the parts of the image that don't have really information, I just discard them, and then I get this new matrix that you see here that essentially gives me the information condensed version of the 3x3, and then I compare this with a set of filters of what that condensed image looks like, depending on whether the object that we're looking is an X, an O, a forward slash, or a backslash. And then the arithmetic number, that the higher score is the fit. But this is all probabilistic, you see? I mean, the important thing is that it's just going to give me a probability, a number. So in this particular case, if I'm trying to figure out what's this, convolution layer will get rid of the grass and the sky, and it will actually just select the boat, and then it will apply pooling and convolution layers, and then it will compare the kind of extracted part with the pictures of dogs, cats, boats, and birds, and then it will say, well, it looks more like the boat. This is another very nice example in the case of faces. I mean, the first abstraction layer is just strokes of different positions, right? Then in a second layer of abstraction, you go wider, and then you actually have eyes, noses, ears, but that's already something, but this is not enough to classify. In the third layer of abstraction, I'm actually putting together full collections of eyes, noses, and faces, which is actual people's faces, right? So it's very important to realize that, of course, this is super dependent on the training data that you give, right? This is another example. The authors of this network have trained the network with lots of images of people of different sizes, on different positions, lots of cars, and lots of trucks, and even bikes. And then once the network has been trained sufficiently, it can really classify things in extremely fast. You see, it's kind of classifying at 24 frames per second. So it's extremely fast classifying when it's being trained. So what are the machine learning shopping lists? Well, we need to have lots of data, right? We need to have truth labels, and that's very important. We need to be able to tell the algorithm beforehand what's what. And then we need computational resources. It so happens that the ESEC Science Data Center, we do have two of these. We have over 600 terabytes of data from all our space missions. So beautiful data that I'm going to show you in a minute. Which is actually consumed by over 10,000 users who download typically around 70 terabytes per month of data, okay? I would argue there's still a large fraction of them who might still be using the traditional analysis. So we want to kind of arm them with the more sophisticated machinery. And let me tell you now the example of how are we doing this with asteroids in HST data with AutoML. So why asteroids are important? Asteroids contain information about our origin and possibly our end. Okay, so here on the left you can see all the orbits of all the asteroids that we know of. There are today over 700,000 known asteroids orbiting around the Sun. Mostly are in the so-called main belt, which is between Mars and Jupiter. But all these objects are the remnants of the planet formation process. So when the Earth and the planets were formed, all the remaining dust produced the asteroids. So everything we learn about their chemical composition is information, super relevant information about kind of how the rocky ingredients that made the Earth, and therefore that made life on Earth possible. Now, there's
on August
of course
10th,
there's a component,
our planet will have
which
a
is
close
that
encounter
if
with an
any of
asteroid,
those objects
an
actually
absolutely massive one
due
that's
to
bigger than a
gravitational
100-story
interactions
building.
change orbit
The asteroid,
and then come
called
towards the inner
2006
side of the solar
QQ23,
system,
is
then
more
we
than
might find
1,860
ourselves
feet in
in a
diameter at its widest point.
very
It orbits
difficult
close enough to our
situation,
planet
because
that
as you
NASA
know,
has designated
any of
it
these
a
asteroids
near-Earth
could
object.
actually impact the Earth,
On the 10th,
and if they are
2006
over a kilometer in
QQ23
size,
is
they could
expected to hurtle
actually
past
kill
Earth within about
all
4.6
life on
million
Earth.
miles of us.
And there is
The
this
closest
joke
call
that I've
since
seen
2001.
there is a
4.6
man
million
from
miles
Israel
might
that
sound
says
really far
dinosaurs
away.
didn't have a
And
space
rest assured
agency,
that
right?
2006
So we need to protect the Earth
is indeed
against
expected
the
to pass us without
eventuality
incident,
that some of
but
these objects
that's
will
still
actually
close enough
come
that NASA considers
towards
the
us.
asteroid
So as you can
potentially
see,
hazardous.
asteroids
That's
give
an
us information
uncomfortable
about
thought,
our origin,
especially
and it
considering
also
the
might
asteroid's
also give us
size.
information about
If
our
it did
end.
crash into
So
Earth
we really
someday,
want to learn
the
about
force of
these
the collision
objects
of the enormous
as much
rock
as possible.
could have.
So asteroids in Hubble images actually appear as curved trails. You can see on the top right here what asteroid trails look like, and that's because of the relative movement of the satellite of the asteroid flying and Hubble. On Hubble itself. Sometimes you see these curved trails. So to find them, what we did was to create a Suniverse project called Hubble Asteroid Hunter, where we showed people images and asked them to classify. We asked them, is there an asteroid trail visible in the images? And then here you can see on the bottom left, right part of the image, there is an actual asteroid trail there. So people had to say yes or no and mark the positions. And then once we had this, boom, we found lots of very nice asteroid trails with crazy shapes. I'm going to show you lots of these because we found them fantastic. All these little yellow points are the markings from the volunteers. And then actually we have just discovered that actually trails are also visible in HST raw frames. And there was one of the volunteers, Melina Thevenot, who actually found one such asteroid flying in foreground, passing foreground of the Crab Nebula, which is of course completely unrelated object, you know, a huge distance away from this asteroid trail in an incredible cosmic coincidence, right? But then there were also false positives, right? We've seen cosmic rays that people have classified as asteroid trails. We've seen gravitational lens arcs, which are fascinating objects I'm going to show you about in a minute. And then we've also seen these very long trails, which are actually due to satellites, like artificial satellites, not actual asteroids. And talking about gravitational lenses, so what happens in these cases is that there is a huge gravitational potential, there's a hugely massive galaxy or a cluster of galaxies that it's distorting the light of a galaxy that it's sitting behind. So you see all these blue arcs around the center of the images here. These are distorted images of super far away galaxies that have been amplified by this galaxy cluster acting as a lens. That's why they're called gravitational lenses. And believe it or not, the volunteers have found no less than 200 new such objects. Even if we were asking them to look for asteroid trails, there's so much information there. And there's actually, there were only 1,000 such objects known. So, I mean, out of existing data, we've increased enormously the information about this type of objects. So how does it, what are we doing? We've been using Google AutoML. This is how, essentially, this just identifies and classifies the objects. The interesting thing about AutoML is that the algorithm itself defines the network based on its performance. So it defines a so-called cost function, and it optimizes it just to have the best possible rate of hits in the right types of objects. So you've seen a bit the convolutional neural network with the convolutional pooling and connected layers. Here you have the structure of one of the networks that AutoML produced to be able to cope with this Hubble data. You will see some convolutional layers, some max pooling layers, some reshaping layers, and all these branches. These are all the things that the algorithm itself decided that it needed to do to be able to cope with the variance in the data. When we saw this the first time, we were really shocked, right? Because this is such a huge level of complexity that, obviously we can't really expect to be able to do this by humans only. Now let's see how it works. We fit it with 1,300 asteroid images, 1,300 cosmic ray images, close to 500 gravitational lens arc images, and 1,600 satellite images. And it did classify lots of asteroids. You can see some of the trails in the top row, and some satellites that you can see in the bottom row. Just to deal with these things, you need to understand well what the precision and recall. Precision essentially is how many selected items are real, are good, and then the recall is your completion, right? So with all labels, we had a precision of 84%. These two numbers, you need to find a trade-off, right? Because either you are very precise, but then you need to draw the kind of dubious cases, or you get many cases, but then your sample is dirtier. When we just search for asteroids, our precision is 80% and recall is 63. You can see some examples here on the right. When we just search for satellites, which are very easy to identify because of these long trails, precision went up to 92%, which is excellent, and 86% recall, which means we're finding 86% of everything that might be there. And then now we compare humans versus machines. And then actually here we have a few examples of asteroids that the humans identified with the yellow outlines, and then the computer identified as well, more or less in the same position, with the same category, right? You see here some gravitational lenses and some satellites. Now, imagine what's like actually doing this by hand. I mean, you have to go and search one image and then another one to look for these little trails. Okay, so as you can imagine, I mean, it's very consuming, but one of the virtues of these algorithms is that they're crazy fast. So what we did was to actually classify the whole Hubble archive with this algorithm. Essentially, we had 40,000 composite Hubble images from the ACS and Wide-Field Camera 3 instruments, which we had to split in 4 quadrants because they were too large. We needed to use 122 computed no hours to train the network. Then we ran on multiple nodes for around 3 hours. And then here's the good news. The batch classification of the whole archive took us 7 hours, which is 38 node hours in several nodes, and it costed us 60 euros. And then we have run our classifier through the whole Hubble archive. Now, what have we found? Okay, we found 2,400 asteroid classifications. We've determined that around 5% of the images contain asteroid trails. 1,200 are actually the ones that humans found, okay? But then there are 1,200 new ones, right? Out of which around 1,000 are new ones because based on our precision of 80%, okay? So we found 1,000 new asteroid trails. We can now, with the positions and the times when it was observed, we can go to the minor planet center and actually figure out whether these are known objects or not. Actually, 700 are actually identified, okay? Which is only 30%. It means the other 70 are new objects. I mean, we've just discovered lots of asteroids with existing archival data by using this method in a way that we couldn't have done by eye, okay? The vast majority are the main belt, as I told you, this range between Mars and Jupiter, and then 70% of the trails are new asteroids, right? So we need to kind of, there are new, are discoveries really. Their magnitudes are pretty high, which is in astronomy the way to tell these are faint things, okay? This histogram shows you the range of magnitudes from all the known asteroids, these many thousands, hundreds of thousands of known asteroids. They are in this range of brightnesses, okay, between magnitude 18 and 24, but all the ones we're finding are on the order of 20 plus, right? So they're fainter, right? And that's very exciting because these are things we couldn't have found. Satellite trails, we found 38 observations with satellite trails. Around 10% of them have, around 10% of the Hubble images, composite images, contain satellite trails. And check this out. As I said, there are many of them. 3% of the raw images actually have them. And look at these examples. The one on the top left is a satellite. That flew very close to Hubble, right? That's why we see such a big streak here, right? So this was just a few kilometers over Hubble's orbit, and it was just it so happened it was observing that direction, and then phew, this thing flew through. On the top right, you see this streak with this kind of punctuated flashes of light. What's that? Is it beeping? What is the satellite doing? You know, we're just seeing that there. Some of them do rotate because of the same parallax effect that I mentioned for the asteroids, and then we see lots of others. Of course, we could play the game of trying to figure out, okay, now we know the orbits of these things, so we could figure out which satellites they are, but then we are probably getting into some sort of military, secret area because, maybe these satellites are not, civilian, right? Then there's even more things. The network also found these asteroids, and then when we checked them, we found that they were actually intermittently bright, right? You see here one on the left, you see a detection of one asteroid with a 90% chance, but then it's followed by a second one that the algorithm didn't find, but it's obviously there. So there's obviously something that is rotating, and it's only visible at certain phases of rotation, right? So lots of fantastic stuff that we've just done by training this network and running through the archive. How does it all fit into our data center? So essentially, this is part of a larger plan, of course, where we want to enable all this data science. In particular, this thing I've been presenting is deep learning classification of images, right? Such that we can allow people in the future to explore data automatically, right? There are several other things. We can apply the same for quality control. So for identifying, glitches or problems in the images. We are also working on a method to kind of denoise the images such that they're sharper. We're also linking data and papers, and then we're finally creating virtual assistants that will actually chat with people to help them going through the data. Essentially, what we want to do is to go from a current situation where we just receive the data, index it, and ingest it into a new phase in which we will actually classify the data with these machine learning models before we ingest them, such that then people can search based on them. So what the future might look like? Well, we know science is not really kind of a linear process. It's more like, okay, you start, which source should I use? Is the data well processed? So it's kind of this random path from the idea to the paper, right? So what we believe is that the most advanced ultimate data query system should enable a dialogue with the user, okay? Like in this movie here. So what did this dialogue would look like? Well, in this application, the sky would look like this. Could you please tell me where are there interstellar bubbles? And this is the result from another example. And then the application will, boom, put in the screen all these red rectangles, which are machine learning classified ISM bubbles in the Herschel data in particular, okay? And because this is done automatically, this is an earlier project that we did together with Maggie, we found thousands of these bubbles, right? Not just the object I knew about, we found thousands of them. And we can compare them, and we just feed the whole archive, the whole Herschel archive here. So you can see all of them, you can inspect them, and then you can now compare them with bubbles that you know of from the literature, say, and which are now painted here in green, okay? So these are bubbles that were identified by citizens of another citizen science project called the Milky Way, okay? And then you can compare, the bubbles that were found, the bubbles that were known, the bubbles that were not. And then, as I said, then you can compare, let me scroll forward, you can then compare this with papers, right? You can then say, so how these things, oh, for example, you can filter by probability, right? Because all these things have a probability of being the object you were looking for. So you can say, okay, just show me the 90% likely ISM bubbles, and this is what you have, which you can compare them with the human labels, and then you can compare this with the literature, right? You can say, okay, let's check how many of these new ISM interstellar medium bubbles that I have found with my algorithm have been published about. Okay, so just to finalize, take-home messages. You see, there's huge potential. Enable data-driven searches in ESA archives requires prior classification of all the data sets with known labels of known contents of the archives, either from our mission expert scientists, from citizen science projects, or by using unsupervised machine learning algorithms, which I didn't describe, but we're looking into as well. Our first supervised classification experiments have shown fantastic results in terms of classification reliability and processing speed, demonstrating the feasibility of enabled data-driven searches in ESA astronomy archives in a relatively short time frame. Just to give you kind of a final piece of information, this final batch processing classification of the whole Hubble archive happened last weekend, right? It was Pablo who just finalized classifying and ran the classification, and we found so much information there, right? So I think this is all I wanted to tell you. We think there's kind of huge future. The background, you can see kind of the manual version of searching for asteroid trails, which, as you can see, it's a bit more time consuming. I think I would stop here, and I would take any questions. Thank you for your time.
Thank you, Bruno, for this very nice presentation. So I can see two questions. One from Fabrizia. The probabilistic aspect that you mentioned in your talk, is this related to the softmax activation function in the output layer?
Yes, of course.
If not, can you? Yes.
Yeah, I didn't have time to explain too much that in detail, but yeah, of course, all the in this deep learning network, all the steps from one layer to the next one is probabilistic, and it's based on and the indices and the hyperparameters of all these transitions are depending of certain thresholds that are updated with more data, the more data you give to the network for training. I don't know whether this answers the question, but yeah, of course, it's all probabilistic, and it all depends on the kind of data that you feed the algorithm.
Okay, thank you. There is also a second question from Beatrix. How do you make the distinction of the type of object, asteroid or satellite? Is it just based on the length of the streak?
So this is a very good question, and that's actually in the core of what the work that is needed on the work that is needed for this to work. Essentially, we combine our expert knowledge on the Hubble data together with the classification from citizen scientists. So essentially, what we want is to capture our own expert knowledge on interpreting what the data is, such that just to kind of encapsulate this into a machine learning model, such that we can do this at scale. So yeah, there is the at the end you need a first step where humans classify a good collection of images as a training sample, such that then you can then use the model to search for all the same occurrences of the same type of objects for the whole archive.
So So thank you, Bruno. I think time is over.
Sure.
Thank you again for your very nice presentation, and you have a lot of congratulations for many people about it.
Thank you.
So